Okay, I think we'll get started. So today we're going to talk about chemical potential. And this will be a rather short lecture. This is something that's not in your book, but again, this is one of those that I think is so important to start understanding that I wish it were in the general chemistry books. It really is the key idea for thermodynamic equilibrium. And so it's just sort of, I guess historically, we've developed chemistry thinking that chemical potential was too much of an advanced topic, and we don't even include it. But I do want to talk about it in this sequence, and especially since we're focusing, we're not just general chemistry, general physics, we're focusing on getting ourselves ready to really understand physical chemistry, and chemical potential plays a huge role there. So let's back up a step and say, okay, we've talked about work. We can always cast work in these generalized force, generalized displacement. Now, we've talked about, or we've seen, that there is a generalized force, generalized displacement that involves chemical work, and that is a chemical potential times a change in the number of moles. And if we don't have any other kind of work, then we have this. Now, what is chemical potential? Well, we can think of it as the potential to change the amount of material. So one analogy is it's very similar to voltage from a battery. So voltage from a battery can drive a charge, so it can change the amount of charge, or it can push a charge. The chemical potential, much like the electric potential that is a voltage from a battery, the chemical potential is it's the propensity to push molecules either in or out of the system. And this is true for a single molecule. It becomes very important when we talk about chemical reactions, where you can turn one molecule into another. The balancing of those chemical potentials are what decides if that's going to happen. All right, well, chemical potential does come with a number of things that we have to talk about. And so chemical potential, let's look at the units here. The units are energy per mole, because if we multiply by mole, we get energy here. So it's energy per mole. And since it's an energy, it is not on an absolute scale. So we can't talk about the chemical potential. We always have to talk about the chemical potential relative to something else. Well, that something else generically is called a reference state, and one of the most common reference states is something called the standard state. The standard state is where we have 1 atmosphere of pressure, 298 Kelvin, and everything is 1 molar if we have and we haven't talked about, we have talked about concentration. So 1 molar concentration, say, in a beaker, if we're doing a reaction in a beaker. And then there's this crazy activity over here. And this is not in our books, and we don't need to talk about it yet. It is definitely very important. But it is capturing the way the chemical species behaves in its current state. So that might be very different than some idealized case. Now, to a good approximation and to just get some ideas down, in general chemistry, what we normally do is say, no, things are behaving like an ideal case, in which case the activity is just replaced with either the concentration or the pressure of that particular species. And so we reference to the standard state, and how we deviate from that standard state is given to us by some function of the concentration. Right? So what is our concentration compared to the 1 molar concentration? Or what is our pressure compared to the 1 atmosphere pressure? And it just so happens that it's plus RT log K. Now R is the gas constant. So that's a fundamental constant of nature. You can just Google that. and it's in SI units, it's 8.3 joules per mole Kelvin. And temperature, and T is just temperature. All right, we can put this in the form of the first law. So if instead of talking about pressure volume work, we're talking about chemical work, then du is TdS plus mu dN. All right, so that's chemical potential, and we're going to come back to this after we do a lot with sort of the details of balancing chemical reactions, understanding the equilibrium, calculating things about equilibrium for chemical reactions. But when we come back and talk more generally, chemical potential will be the heart and soul of that. So let's just start with not a complicated reaction, just A goes to B. Now, if we have just A and B in a container, let's say now we have a container of gas rather than concentration, then we write a chemical potential for each species. Right? If there's 100 species in there, then there'd be 100 of these terms, and the du for this would be TdS plus mu A dNA plus mu B dNB. Okay, just like that. Now, if these are just sitting there, that's all we would have. If there's a reaction, then that shows that these are related. And what we like to look at is the difference in chemical potential of the products and the reactants. So the products minus reactants here. And in this case, very simple, just mu B minus mu A. So let's write mu B minus mu A out in terms of what these are relative to the standard state. And when we do that, what we see here is that on this side, that's just our delta mu. But what's going on this side? We can connect here. What do we have this? We have a mu B standard minus a mu A standard. So that's products minus reactants at standard conditions. And so that's this here. This is a single value independent of where the reaction is at this point, because this is saying what is the difference in the way we want to change A versus the way we want to change B when everything is 298 Kelvin, 1 atmosphere. Then we're going to use a little property of logs here. So let me write this out. This is RT ln PB minus RT ln PA. So we have a RT as a common factor, so we can factor that out. And then we get ln PB minus ln PA. And now we're going to use log of A plus, or minus log of B is log of A over B. And so this becomes RT ln PB over PA. And we're going to see this very shortly. In fact, I think in the next lecture here, we'll see this ratio of either the partial pressures or the concentrations of the products and the reactants. All right, so this was kind of a brief lecture. There's no homework on this, but I just wanted you to start to hear these words: chemical potential, not so much activity, but chemical potential, how it's related to what we've been talking about so far, and then getting ourselves set up to how it will be related to when we develop the most important equation in equilibrium, chemical equilibrium, and that is the delta G equation. And this is intimately related to that.